this. A lot of my family lives up north. It's going to snow up there, up north Georgia, possibly Thursday. We might be snowed in for a few days. I don't think it'll be that bad here. But maybe we'll get some snow over the weekend. So it feels kind of weird that partway through the second weekend I have not lectured at all yet. This is really the beginning of the class. So I did ask people how many of you took chemistry before, and most of you did in high school somewhere. But this class is designed to start at the very beginning, so I'm guessing a lot of this is going to be familiar. It should. Significant figures. Make sure the video is going. All right, so I will upload this PowerPoint. Significant figures. How many of you remember at least that phrase, significant figures? Sometimes called significant digits. I'll just say sig figs a lot just because it's easier to say. But before I start writing numbers on the board and start talking about significant figures, you can think of it like this. There's a thing to consider for significant digits when you're the person writing the number down, like you're the person making the measurement. So you have to make the measurement and get it written down properly. And then another way to think of it is you're walking up and looking at one that's already written down, and you have to determine what are the significant figures that person wrote down. Let me start by showing you what it's like when you are the one making the measurement. I'll just do that real quick, and then that's really a better starting point for being able to just determine what the significant digits are when you walk up to a number and look at it. So look at the PowerPoint here. So the first, I want to say this out loud. The name of the PowerPoint that I'll upload is just going to say sig figs. But you're looking at a cylinder there, so that's one way you might make a measurement, and we'll certainly make measurements with cylinders. If you looked at that, and you pulled out your pencil and you said, okay, I'm going to write down what this says. First of all, maybe you know this, but water makes that curvature. And when you make the measure, you measure it at the bottom of the curvature. That curvature is, you might know what that's called? Meniscus. Fancy vocabulary word. So right at the dip of that curve point, you look at the scale, and now you're going to write down a number. What's the first digit you're going to write down? I'm going to read that, I'm going to write it down. I'm going to say 2. And you kind of have to look at the scale to decide what the tick marks that aren't labeled are. You see it goes 10, and then tick mark, 15, and tick mark 20. So the tick marks are 1, 2, 3, 4, 5. So each one, so we're up from 20. What's the next digit I would write here? Can you see that we're between 21 and 22? So you're at least 21, so you're going to go, it's 21. This digit definitely would not be a 2, so we're at 21. And you always do this when you make these measurements. As long as there's some distance between the lines, and I guess I'll draw it. You've got a meniscus doing something like that. I would do it be a little line too. So you've got 20, and I didn't draw that very well, but whatever. And you've got this. No, it's a little higher than that. That's still. One more try. So 21 is not written on there, but you infer from the scale by looking at the whole scale. That's 20, that's 21, that's 22, so we're at least 21, so we write down 21. And then you put a decimal. And now you actually look here, and you try to envision 10 tick marks going from here all the way up to here. And if you look at that, you can generally make a good judgment here. So you always get that last digit. Would you be tempted to put a 5 there? I mean, this would be like, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 10. I know that's not perfect. But what I'm getting at is, that's not swooping down right in the middle of these two, is it? So you're definitely probably not going to put a 5. You're going to put something definitely 5 or greater, right? You're definitely not going to put a 1. You know it's not there. You know what I'm saying? That last digit is actually a pretty good estimate. What would you put for this? 7. A few people might do 0.6. If I had 1,000 people read this, there might be a tiny number of people that put an 8 here, and a tiny number of people put a 5 here, but most people are going to put one of these, don't you think? So it's not perfect, but it's a pretty good estimate of where it is. So the person reading this would write down something like this. That last digit has a tiny amount of uncertainty with it, but it's still pretty good. So you always make your readings like that. The other thing I want to say on here is, what if yeah, that's what I just said, the second slide. 2 and the 1 are certain. 6 is an estimate. Some people might say 7, some people might say 5. But let me leave that diagram there and say, what if the meniscus did this? I'm trying to get it right on the line. All right. So you would probably walk up this and go, that's 20, that's 21, that's 22. So we're definitely at 21. Just the mere fact that you know there's some distance here that you can estimate, you still want to write a digit for this. What digit would you write for this? You would put a 0. So I'm trying to account for the fact that sometimes there's zeros on the right side of the decimal, and sometimes they're not. But let me put it like this. If we could zoom in, so we can zoom in this close by looking close and see that it's right on the line. But what if we could zoom in again and we found out it was right on the line again? I mean, what if we could really look down here and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we turned out it was still on that bottommost line there. Then we would put another 0. If we could zoom in again. Generally you can't. You can only get that far. But my point is, these trailing zeros, whenever you have a number like this, go back to your arithmetic class, your first arithmetic class where they start talking about decimals. Truthfully, there is an infinite number of zeros to the left, not this way, but we never write them. Why bother, right? No one ever writes those. Those are easy to deal with. Point, let's go back to the 0.6. Negative, or out to, not infinity, but there's an infinite number. And then this goes out infinitely. That's supposed to be an infinity symbol. You might have learned that in arithmetic, that technically there's zeros all the way out to infinity there. But in our case, where we did this one that was 20.1, technically there's infinite numbers of zeros out there. But the reason I actually wrote this one is because I did actually measure it. You see what I'm saying? It really was right on the line. That's why that 0 is there. That's why, as the writer of this number, I actually wrote that 0 there. I mean for the person that reads this to realize that definitely means something. It's just not a placeholder. It's not just a placeholder for all these zeros. I chose to put that 0 there because it counts, because I did actually measure it. You see what I'm saying? If I read this as 21 and just left it like that, I've done something wrong. I've left this extra piece of information out. So 21.0 is what I want to write down. What if this was a smaller cylinder and this was 2? Yeah. What if that was 2 and then this was 2.5 right there. And if this was a scale, this would probably say 2.0. Now what would you write down? You'd go, it's not 2, and it's not 2.5. You would write down 2.1 for this. And then you would stop there because you can't read any, 2.1. Yeah. You would not stop there because this is 2.1. This is 2.2. This is 2.3. And in my other example where we had a meniscus like this, you would write down 2.1. There's 2.0, 2.1, 2.2, so you would write down your 2.1. And then to estimate this last one, then you would put the 6 there. If that actually looks like a 6 to you. I'm trying to make that look like it's a little more than halfway. You see what I'm saying? Like 6. But in the same way, if you had the meniscus like this, you would go, there's 2, there's 2.1. And you would go, okay, in between here, I'm going to estimate, oh, it's right on the line. You would actually put a 0 there because you can actually measure it. You see what I'm saying? If it was right here, I would put 2.16. But since it wasn't here, it's down here, I'll put 2.10 because I really do need that 0. I actually measured it. So as a proper recorder of information, I make sure I put that 0 there. So when somebody else comes and picks up that number to do something with it, they go, oh, that actually counts. They measured that. That's not just one of those infinite zeros that go out there. The writer of the number was telling me that actually hit the line. It looked to them like it was right on the line. That's where trailing zeros arise for a person making the measurement. See what I'm saying? That's why they're sometimes significant. Let's go to, let me expand this a little bit. I'll upload this PowerPoint, but I think I'll do most of my explaining by just writing numbers on the board. And let me say this first. The only thing that makes significant figures confusing, I promise, is the zeros. That's the only reason significant figures are ever confusing at all. Now you're the role of the person walking up to a number and reading it, and you're trusting the person that wrote it did it properly. If you walked up into this and you said, how many significant figures are there? It's easy. Every digit there is significant. There's no zeros to deal with. 1, 2, 3, 4, 5, 6, 7, 8. That's, did I say 8? 8 significant figures there. That's how simple significant figures are, without zeros. The next thing to say is, your text calls it, I say sandwich zeros, they say captive zeros. If I have a 0 here, between two non-zero numbers, and let me just throw one in here. If it's got non-zero digits on either side of it, it's significant as well. But that's kind of obvious because a number has to be contiguous. So you can't go significant, significant, not significant, then significant again, significant again. It's only this very last one that's uncertain at all. So if you've got a number written like this, sandwich zeros, captive zeros, those count. But really, that's because your significant digits are always going to be contiguous. You can't go from being significant to unsignificant and then significant. See what I'm saying? So captive zeros always count. Those aren't the confusing ones. You follow me? Another way you see zeros is you might see that's what we call leading zeros. Those never count. Those never mean anything. And that's kind of obvious too, right? In fact, if someone made a measurement and it was 34.613, they're just not even going to write those. You know what I mean? People usually don't even write those. See what I'm saying? All right, another type of leading zeros you might see. These are all still leading zeros, even though I've crossed over the decimal point. If I can start at this 0 and then everything to the left of it is zeros and there's no non-zero digits, then none of those count for significant figures. And so here's an example of leading zeros. They're not very good circles. Here's two examples of leading zeros. This one doesn't cross the decimal. This contiguous set of zeros does cross the decimal, but either way, they're not significant. They don't count towards anything. You follow me? Allow yourself to see this as obvious. I haven't gotten anything sticky yet when it comes to zeros. Sandwich zeros, they're always part of the contiguous number, so those count. These that are leading, if you put your finger on the rightmost zero, and it's that one, and everything to the left of it is 0, those are all leading zeros. This one, everything's 0 out here. Everything's 0 out here. Another way to say this is from now on in this book, proper scientists don't write numbers like this. You might see, you ever see an old, they're all digital now, but old gas station pumps that have little flip things. So if the one on the left might be 0, and the next one on the left might be 0, but they're just there in case a number shows up, like you get up more than 10. You've never seen those, have you? Those are that old clocks used to do this too, but everything's digital now. Never mind. Anyway, so you don't see scientists writing stuff like this anyway. If the number were this, a scientist would write. So scientists do sometimes list leading zeros. But if it's down here on the right side of the decimal, we'll just write a 0 here, point, and then if these are zeros, we write zeros, and then we start writing our numbers. That's probably the case that you would see leading zeros that don't count. Probably the only case for the rest of this book, because that's the only thing scientists ever write. Scientists wouldn't write more zeros than that on the left side. There would be no reason to. So just in case there's some examples in this book that are like that, just realize they're silly examples, because no one does them. If you see leading zeros on the left of the non-digits, you're probably going to see this. You might see this, but still, if it goes across the decimal and there's nothing up here on the left of the decimal, they're only ever going to put 1 0 there. There's 4 leading zeros. Those don't count as significant figures. There's 1 leading 0. It doesn't count as significant figures. You with me? So allow yourself to see this as obvious. Leading zeros don't count. And it's more typical to see this in science than anything else. Here's where confusing zeros are confusing. And here's the whole point. You're not the reader of the number. You're not the recorder of the number now. You're in the other role. You're walking up to somebody else's data. If you walk up to their data and you see this, you know that that counts because they measured it. They wouldn't have written it if it didn't. You're assuming they know how to record data and read a frequent scale. You see what I'm saying? If they wrote it, it's significant. It counts. They actually measured that. And if they couldn't measure anywhere below that, then they're not going to write it. See what I'm saying? Do you? I just nailed that song. You guys follow that? That 0 on the right side, we call these trailing zeros. And what I mean by trailing zeros means specifically, if that's the number and there's nothing after the decimal, Those are trailing zeros, but they're on the left of the decimal. The decimal would be right here. I mean trailing zeros on the right. I haven't talked about these yet. I'm talking about trailing zeros on the right side of the decimal. Trailing zeros on the right side of the decimal always count. Because you're the reader of the number, and you're assuming the person who wrote the number knows what to do. If there's a zero there on the far right, it counts. And in some applications, there might even be two zeros there. Pretty rare in the real world. But if you see two trailing zeros, but not another one, no, those both count. That means the person who wrote this number, it was right on the line, and then they zoomed in again and looked real close, and that one was also right on the line. Here's how sandwich zeros show up. They look in, it's right at 0, and then they zoom into that last tiny bit, and this one turned out to be a 2. But of course, like I said, it has to be a contiguous number, so sandwich zeros always count. But if you walk up to a number and it's like this, both of those count because they're there, because somebody wrote them. The theoretically infinite zeros out here, the writer of this number didn't write those. They knew that. Those don't count. See what I'm saying? So this is the first kind of confusing point when it comes to zeros. On the right side of the decimal, if they're there, they count towards significant figures. You with me? Let's talk about zeros on the left, because it introduces another convention of indicating significant figures. And it is kind of simple. All right, 3,500. So, it's kind of a mouthful, but I'll say trailing zeros. Trailing zeros on the right, no, trailing zeros on the left of the decimal, but on the right of a non-zero digit, like these. If a person made a measurement, and these were the only things that were significant, but these weren't, like in that case, they just wouldn't write them. But if it's on this side of the decimal, that looks like 35 instead of 3,500. They have to write these zeros. These have to be there to see the magnitude of the number. So there's a magnitude of a number. That doesn't change its magnitude. That doesn't change its magnitude. That doesn't change its magnitude. But these change the magnitude, and you have to put them there. That's not the way it was. So the convention is, do y'all remember this from somewhere else? Difference between these two? If a person made a measurement, and every one of these they measured, then they put a decimal here. This decimal is telling you that these zeros just to the left of it are significant. If they don't put the 0 there, that means only these two are significant and they couldn't measure these other two. You with me? So there's one point of confusion trailing to the right. Another point of confusion, this is still trailing to the right, but still to the left of the decimal. And in this convention, you put a decimal there if the 0 counts, and you don't put a decimal there if it doesn't. Another example, 230. Here someone made a measurement, and they looked a little on the next tenth of the scale, and they measured this, and then they couldn't measure anymore. But they had to put a 0 there because it's 230, not 23. In this case, someone looked at a scale, and then this one was a 3, and then they were able to look a little closer and go, oh, that's right on the line. And they want the reader of the number to know that all 3 of those were measured. Where in this case, all 3 of them weren't, only these 2 were measured. You follow that? And that's kind of it when it comes to significant figures. That's all you need to know. The next thing I have to segue into is scientific notation. But let's go over some significant figures first. I don't think I put any in here. Addition, subtraction. Let's go to so looking at 48. I'm going to do 48. 49 is the same. But those are you can use for practice because you get the answers to that one. In the back of the book somewhere. Some of these have scientific notation. I'll come back to those. And you could ignore the units for these. Okay, there is something very easy about this one. Why is this one so easy? There's no zeros to deal with. When there's no zeros, you just count everything that there. Let's say this is 3 significant figures. Significant figures are a statement of precision. So you could say that's 3 digits of precision. If they measured this one, that would be 4 digits of precision. So 3 digits there. How about this one? How many significant figures are here? 1, 2, 3, 4, 5, 6, 7, and all of them count. That's a column A. All of these count because those are sandwiched. There's no trailing zeros. There's no leading zeros. There's no the decimal is here. They just don't have it written there. But it's 1, 2, 3, 4, 5, 6, 7. That's 7 significant figures. You see that? That one's 7. There's no confusing zeros. So all of them count. The next one, how many significant figures are here? The decimal right here. Below here, and someone else recorded this, and they wrote that 0 there. So how many is that? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, and this one counts, 6. The writer of this number would not have put that trailing 0 there if it didn't count. You see what I mean? How about this one? How many is it? 3. This one's 3. These are leading zeros. Starting at this 0, going out to the left, everything's 0 from here all the way out. So that's a leading 0. So none of these leading zeros count. This one is 3. You with me? Anybody feel lost? Most of you, this is a review, but if you've never seen this before, speak up if you're feeling lost. How about this one? 3. This one's 3. The writer of this number would not have put that there if it didn't count. So this one's 3. How about this one? Yeah, whoever said 4. These are leading zeros. Those don't count. You got a 1 and a 4, and then the writer of this number put those there, so they count. So that's 4. Significant figures. You okay? So expect on the test to see just a bare number, and you tell me how many significant figures you see. And at the back of the book here for practice, you can do 49. I'll come back to scientific notation, the powers of 10. But I think it's better to just start where I started. The next thing we do, I guess we could do these. Look at number 50. A, how many significant figures are there? 0.0055. That one's 2. The zeros are all leading. B, how many significant figures? 2. There's no zeros to deal with, so every digit is significant. So there's 2. Percent is actually a unit, so you can ignore the percent. For C, what is C? It's just 1 significant figure. D, 2. E, 3. F, 3. G, 1. Just 1. That's got some leading zeros on it, but that last one is the only significant figure. H, 4. Trailing 0 on the right side of the decimal. It wouldn't be there if it didn't count. So that H is 4. I'll after I do addition, subtraction. So I'll upload this PowerPoint. There's not a whole lot in it. But slide number 5 on PowerPoint, it will be called Sig Figs. So you have to sometimes do multiplication, division. You have to sometimes do addition or subtraction. And there's a way you treat the answer based on the input values for significant figures. After all this time talking about significant figures, it helps to start with the multiplication division rule, because that's based on nothing but significant figures. Okay, so what you do, this is the way I always do this. I do it when I'm sitting at my desk. I do it when I'm doing it on the board. I will do it in my calculator. By the way, you guys will have to use these calculators that are hanging on the wall and tests, so you want more practice with calculators like that, just to make sure nobody brings a calculator that can save notes and do formulas and all that. 19.6 times 31.1. It doesn't matter if I put the 0 in the calculator, but I will. Here's what my calculator says. So what I'm saying is, I always write down everything my calculator gives me, and then I go from there. What you do for a multiplication division is, how many significant figures are here?
3.
How many are here?
4.
This one's 4. That's a trailing 0, and it does count. Your answer has to have the number of significant figures that's the least number of significant figures in your input value. So we're going to put 3 in there. So you have to round this off to 3 significant digits. The way I always do this is I'll underline the first 3 digits and go, okay, those are the places I'm going to keep. You look one more digit out, and you decide whether you need to round this. So I'm sure you know this. 5 and up, you round this up 1. And if it's 4 or less, you just leave it as is. This is not a great example because it's a little confusing, but I need to round this up. 609 rounded up 1 to 610. You see that? If I round the 9 up, that kicks this up 1, and this becomes a 0, so maybe this wasn't a great example to start with. But I'll give you another example that won't be that confusing. But let me say this. I need to represent this as 3 significant figures because of this. So what's missing here? Now, that shows 3 significant digits. So now when somebody else reads the results of my calculation, they know that that's 3 significant figures. That's only showing 2 significant figures. I'll get a different example. That's not great. All right. First thing you do, you just put it all in your calculator. 403.9 times 0.0314. You really don't have to put the zeros in a calculator. The trailing zeros. That's what my calculator says is the answer. But I'm not done. I have to fix this up for its significant figures. How many significant figures here? How many here? There's 5. These don't count. These count. And the writer of the number put this here, so those are 5 significant figures. The lowest number of significant figures is 3. That's what my answer needs to be. So 3 significant figures, it's those 3 I'm keeping. I look one more digit out, it's an 8. So the 8 rounds the 7 up. So my answer is That's my answer. 3 significant digits. I take what my calculator gave me and I rounded it to 3 significant digits. This is multiplication division rule. I guess I should do a division rule. Let's see. Divide that by. There. Start by putting it in your calculator. 34.90 divided by 0.0041, and my calculator says how many digits your calculator gives you is just based on how wide the screen is. It'll give you everything that's there. How many significant digits here? Yep. How many here? This is 2. These are all leading zeros, so that's 2. So I need this answer to round to 2 significant figures. The 2 that I'm rounding to is these. I look one more out. The 1 does not round to 5. And the decimal is here. So I'm going to put 8, 5, and I've got to put a 0 and a 0 for these. And then I'm just going to leave all these off. This isn't correct though. I wrote the decimal there to help me decide how many zeros to put here. If I want this to be 2 significant figures, I have to do that. That's the proper answer to this. 8,500 without a decimal. You with me? What I need to do, I'm not really using my PowerPoint, which today I'm not. I need to keep it there just so people in those back corners can see something. So remind me to put the video back on the screen if I keep forgetting. So this is multiplication division. You do another division. I'll do. Let's do. Something crazy like that. So 0.00314 divided by 10305.50. My calculator says these iPhone calculators will change their scale just to give you all that garbage is what's on my calculator. How many significant figures are here? How many here? 1, 2, 3, 4, 5, 6, 7. 7. So my answer needs to be 3. Use the lowest number. None of these count towards anything. It's these 3 that I want to keep. You with me? I'll look one more digit out. The 6 will round the 4 up, so this needs to be 305. It's 1, 2, 3, 4, 5, 6. And then I won't put anything else there. That's the answer to this one. There's the answer to 3 significant digits.
In that case, would it be okay to write it scientifically?
Yeah, we'll get to that. It's fine with me if you do that. But I'm just going to go in order because not everybody in here has done all this. You follow this? So if it's division or multiplication, your answer has to be rounded back to the least number of significant figures that your input values have. All right. Addition, subtraction seems weird after doing multiplication and division, but just remember that all this talk about significant figures, it really has nothing to do with addition and subtraction. 44.15 plus Pull out my calculator. Again, let me say this. I'm not going to point here and say how many significant figures, and I'm not going to point here and say how many significant figures. That's not how addition and subtraction works. First, though, I'm going to go 44.15 plus 11.216 equals, I'm going to write whatever my calculator tells me. Okay. Now I need to fix this to represent the correct, not significant figures, but this is just what you have to do when you do addition and subtraction. It's after the decimal. This one has 2 after the decimal. This one has 3 after the decimal. So this one needs to stop 2 after the decimal. Needs to be rounded back to there. And of course, yeah, really the rest of this too. I don't mean to exclude that, but I'm focusing after the decimal. This one had 3, this one had 2. The one that had the least number after the decimal, that's where I have to round back to. So I have these, 2 after the decimal. I'll look one more out and I decide whether that rounds. 6 will round that 6. So my answer here is 55.37. And I'm not really considering significant digits here. I'm just looking at the precision past the decimal. See what I'm saying? It's weird. Minus 44.15 minus 1.14631 equals, my calculator says, 43.00369. Okay. Why was I going to say this is weird? This one doesn't come out there. All right. 2 after the decimal, 5 after the decimal, so my answer needs to only have 2 after the decimal. So I'm keeping just those 2, but yeah, I'm keeping everything up here too. But it's really these 2 that I'm denoting. The 3 does not round to 0, so 43.00 is the answer to this one. The weird thing is sometimes, I know what I was going to try to make it do. When I say it's not significant figures, you have to think about here. 44.15 minus 43.991 equals, my calculator says, that's what my calculator gives me. 2 after the decimal, 3 after the decimal, so I want this one to be 2 after the decimal. Trying to avoid that because I think that confuses me. This would be 5 if that goes up to 9 rounds. No, that's fine. Okay. So that's what I'm keeping. I look one more digit out. The 9 rounds to 5, so 0.16 is my answer. But what I'm saying is weird is you had 4 digits of significance here. And here you had 5 digits of significance. I think precision, that's a good precision number. That's a really precision number. But your answer has to only be 2 significant figures. So it really doesn't have to do with significant figures. It has to do with what's after the decimal, and sometimes things are kind of weird. You just feel like we lost all our precision here, you know what I mean? But that happens with addition and subtraction. You guys okay? Okay. I'll go back here. So the back of the book, so rounding numbers to significant figures, I guess we'll do this. But I want to do get to scientific notation. The easy thing about scientific notation, even if I don't tell you how to put something in scientific notation, is in scientific notation, everything you see there is always significant. So we're trying to round all of these to 2 significant figures. So I'll explain this later, but this still works in this context. So our instructions are to round all these down to 2 significant figures. There's 2 significant figures. The 7 rounds to 1, so we get 52. There's 2 significant figures. The 3 does not round to 6, so we can just put 86. You can actually ignore that for this. There's our 2 significant digits. The 8 rounds the 3 to a 4, so 6.4 times 10 to the 23. The answer to that one. 2 significant digits. The 0 does not round to 0, so this is 5.0. There's 2 significant digits. The 4 does not round to 2, so 22 is the answer. There's 2 significant figures. The 5 does round to 8, so we have to go 0.89. So rounding to a specific number of digits. You guys can practice with problem number 53 because you get the answers to these. I suppose you can get the scientific notation, but I think I'll have time to get to that today. It's like literally the next topic. All right. You can use your cell phone for this. Let me have you guys go through this. Calculate 62.8. Just lost A on 54 here. 62.8. And I'll use this calculator. So this is multiplication division. That's the number I get. How many significant figures does that answer need to have? 2. So we got 2135.2. Only the 2 and the 1 are we keeping. The 3 does not round to 1. So our answer to this would be 2200 without a decimal. Follow that? That makes sense? Say again? 22. Oh, no, yeah, I said 22. Yeah, the 3 does not round to 1. So it's 2100 without a decimal. If we put a decimal there, we would have 4 significant. You guys okay with that? Well, let's do the next one is addition, subtraction. This is addition. 0.147 plus 0.0066 plus 0.012. All right, so what's the proper answer to this one? Nope. 0.166. Yeah, 0.166. See, I told you it confuses. You started looking at significant figures. This one has 3 after the decimal, 0.147. This one has 4 after the decimal. And you're looking at it going, oh, but those aren't significant figures. It's got nothing to do with significant figures. It's got how many after the decimal. So 4 after the decimal, 3 after the decimal. So this one needs to be 3 after the decimal. The 6 rounds to the 5, so 0.166. You guys okay with that? Questions?
Why would it not be 2 if you're adding 3 of the numbers and the lowest is 2 significant figures?
Again, it's not about significant figures. It's how many after the decimal. This one that I've got highlighted here has 4 after the decimal, 4 digits after the decimal. I know 2 of them are significant, but they all count as after the decimal. You see what I'm saying? I told you it's confusing. This one's not significant either. This one that has 3 after the decimal, 0.012, one of those zeros is not significant. One of them after the decimal is not significant, but that's still 3 digits after the decimal. So that one is 3 after the decimal. You see that? You guys see that? I guess, I'll let that go away. I guess I'll do scientific notation. Next. So not thinking about significant figures. Actually, no, I'll come back to it. All right. Scientific notation is just a way to write a number. In some sense, it's a way to write a number that's got tons of zeros in it. You get rid of the zeros. Let me put it this way. I'll start like this. I'm going to write a bunch of leading zeros that are silly. Let's see. Three, 4, 1. This is what I want. Okay, 3, 4, 1, 2, 6, 7. All right. I did purposely do the same digits in the same order. That's why I lined them up like that. Are all of these equal to each other? Mathematically equal? Like, can I write this, put an equal sign after it, and write this on the other side equal sign? They're not. They're different orders of magnitude. 341.26 whatever is not equal to 34.1. See what I'm saying? These are not equal to each other. without even thinking of this as some kind of notation, just think of it as a math problem. This is this number times 10 to the fourth. And by the way, I'll do this. I figure you probably know this, but don't think in terms of scientific notation. Just realize 10 to the 2 equals 10 times 10, which is 100. 10 to the 3 equals 10 times 10 times 10, which is 1,000. 10 to the 1 is actually just 10. Do you know what 10 to the 0 is? Any number to the power of 0 for some weird reason is 1. I should have left room to continue up. I'm not in a hurry. 3, 10 to the 2 equals 100. 10 to the 1. 10 to the 1 equals 10. 10 to the 0 equals 1. 10 to the negative 1 equals 0.1. I did something wrong. 10 to the negative 1 is 1. 10 to the negative 2 is 0.1. Because we're starting at 10. So just so you know, that's what these mean. Especially the negatives, if you don't remember, it's just these are less below the decimal. So I felt like I needed to say that. But now my point is, are these all equal now? They are all equal now. This equals 10 to the 4 goes 1, 2, 3, 4. So that would be 341.26736. 10 to the 3, 1, 2, 3, 341.2673. This times 10 to the 2 is 1, 2, 341.26736. See what I mean? If I got those powers of 10 on there, now they all equal each other. All right. Here's what I want to say. Every number here, now that I've written the powers of 10, the appropriate powers of 10 in there, every one there is in what we call scientific notation. Does that confuse you? Those of you who know this stuff? Every one of these is in scientific notation. Does it bother you that I say that? Those of you who know how to do scientific notation, is there one in here that's drawing your eye to it? Go, no, wait a minute. No, that's the one that's correct. No, really? You don't remember any of this? Does this one look special to any of you who have done scientific notation before? But I'm telling you, these are all in scientific notation. Does it bother you that I say that? I'm trying to get you to go, yeah, that one's the right one, isn't it? These are all in scientific notation, they are. This one is in standard scientific notation. Books and instructors do this all the time. You'll catch me doing it too. I'll say scientific notation, but what I mean is standard scientific notation. If you've got a number and you've got a number at the end of a problem, and you've been told to put it in scientific notation, forget what I just said and assume they mean standard scientific notation, because that is what they mean. So I'll do it sometimes, other people will do it, textbooks do it. I wonder if standardized tests do it. It's just a quirk I've noticed that it's sort of lost its meaning. But scientific notation means this. Standard scientific notation means you purposely use the power of 10, that gets the decimal just to the right of the first digit. That's standard scientific notation. So if I got to the end of a calculation and I had, let's say this was the answer to some long calculation I did. This one. And I have 3412.6736. And I'm at the end of my problem and I stop. The power of 10 generally doesn't show up naturally. And then you look back at the problem and you go, oh, this said to put it in standard scientific notation. So then you have to turn this into a number that has the decimal there and a power of 10 that still makes it equal to this. Well, let me just go ahead and do it. 1, 2, 3. Times 10 to the 1, 2, 3. Do you see that those are equal to each other? If you multiply that by that power of 10, which is multiplying it by 1,000, it will equal this. All right, but so you're here and you don't have this, but realize that's your goal. That's what you want to leave for your answer, because it has the decimal just to the right of the first digit. That's your goal with scientific notation, is to take the number you've got and find the power of 10 that represents it, but with the decimal right there. But they have to be equal in magnitude. They have to be exactly equal. Okay. So again, let's say you ended with this number, and you're trying to figure out how to put it in scientific notation. I'll show you this. Any of you already comfortable with doing scientific notation? If you're comfortable with the way you think, that's fine. But let me show you this sort of mathy way I like to do it. I don't always do it like this, but I think it's worth seeing this. Does that make sense? When you multiply powers of 10, ultimately you're just doing arithmetic with the superscript, right? It's kind of like if I had, the answer to this is 10 to the 10. I add the 3 and the 7. If I had this problem to calculate, 10 to the negative 3 times 10 to the 6, my answer here is 10 to the 3. Because you're just doing arithmetic here. 6 minus 3 is 3. Negative 5 plus 3 gives you negative 2. That's how you do quickly multiplication with powers of 10. You with me? You guys know that much? Okay, so let me finish what I'm doing here. So you get what I've done there? If I take a 10 to a power, and then I multiply it by a 10 with the negative of that power, I've got 1. I've just created 1 doing that. You follow that? All right. If I have this number, let me start. No, I guess I'll just keep that. What I'm going to do here is that I'm going to multiply this by a number. I'm going to multiply this by, the whole point is, once you've got it in the correct standard scientific notation, it still has to equal this. It can't change magnitude, so you got to find that appropriate power of 10 that makes sure it stays equal to this, yet has the decimal here. So here's what I can do. I can take this number and multiply it by 1. There, that won't change the value, but that doesn't help me, because I'm trying to get this into a power of 10 where the decimal is here. Instead of doing that, instead of a 1, I'm going to do, I need the decimal here. 1, 2, 3. What I'm going to do is 10 to the negative 3 times 10 to the 3. There. I haven't changed the value. It's still going to equal exactly what it's supposed to. See what I'm saying? But I chose 3 because the place I want the decimal is 3 places away from where it is. So I did 10 to the negative 3, 10 to the 3. And what I'm going to do is, I'm going to go ahead and do that. I'm going to do that now. 10 to the negative 3, 1, 2, 3. And that's still there times 10 to the 3. There. That does it. That gets me to the correct scientific notation. If you've already learned how to do this, what you do in your head is you look at that and you go, I want the decimal here. That means, and I move the decimal back this way, but I want it to be 10 to the 3, not 10 to the negative 3. And this is what trips you up sometimes. You count this way and you're thinking to yourself, to make a decimal move this way, you have to do it by 10 to the negative something. And then you end up putting the negative there. You see what I'm saying? So I just wanted to do that to say there's always that. And I purposely put the 10 to the negative 3 on this side, because I knew I was going to put parentheses around it. But even if you did this, even if you walked up to this and went, I need the decimal there, so 1, 2, 3. What if you did times? Well, that's still perfectly fine because this still equals 1. But now I can't put my neat parentheses around here. So what I want to do is apply this to that number and keep that where it is. So I'm going to multiply 10 to the negative 3 to this. That gives me this. And then this is still there. You guys with me? Are you sitting there going, well, he's really overthinking this? Is that what you're thinking? Okay. Here's where this gets a little more useful. And again, if you're good at this stuff, do it your way. What if I end my calculation and I'm at, that's the end of my calculation, and now I need to put this into scientific notation. There is a little bit more of a twist here, right? You're going to have to go 10 to this, no, that's 10 to the 2, and then you got to add 2 to here, and you're going to do all that in your head. Right? Okay, maybe my babble isn't the way your stream of consciousness works, but here's what I'm saying. Still, you can walk up to this and go, there's my decimal. That's where I need to get it. 1, 2. So I'm going to go there. I haven't changed the value. To do this, 10 to the 2. Just to make this easier for me, let me make that negative 2. This one 2. So now what I'm going to do is, I'm going to insert my 10 to the negative 2 times 10 to the 2 right there. So this is the end of my calculation I had times 10 to the 4. And what I'm going to do is split these apart and put my 1 here. That equals 1. And then I'm going to apply, no, that's backwards. That's only 1. So what I'm showing you is a way to do it with algebra without doing it all in your head. Because when you do it in your head, that's where you make mistakes. I'm inserting 1 here, 10 to the 2, 10 to the negative 2. Why 2 and negative 2? Because I looked here and went 1, 2. I'm 2 away from where I want to be. So I did 10 to the negative 2, 10 to the 2. My 10 to the 4 is still just hanging out here. And now what I'm going to do, I want to hit it right the first time. I know a lot of you are saying, why would we spend all the time on this? Here, that's the way I want it. All right, so I've inserted a 1 here, so I definitely haven't changed the value of my original expression. Now, yeah, that's going to work. I'm going to do that math, and I'm going to do that math. That's still wrong. What the hell am I doing? No, that's right. This equals ignoring significant figures for now. This times 10 to the 4 means this, right? 1, 2, 3, 4. That's what it means. So that's right. So I'm going to apply the math here, which is going to give me the 9.3416. And now I'm going to do this math. So that's what I want. Again, if you like it the way you do it in your head, that's fine. As long as you don't make mistakes, I'm not going to make you show the work and do all this. I just like to show the algebra. You guys okay? When it comes to scientific notation and significant figures, the times 10 to the whatever, every digit here, no matter what you're seeing, is significant. So if you're reading a number, you're not the writer of the number, and it's in scientific notation, everything here counts. Because it's necessarily going to be in the form of so this can't be a leading zero because you had to put your decimal just to the right of the first non-digit zero. And if some of these were zeros, they'll be there, but whether they're zeros or not, they count. So whatever it is times 10 to the whatever, everything you see here is significant for standard scientific notation. All right. I honestly bored myself with that discussion of something. All right. Let's do this. Express these. It's scientific notation with the correct number of significant figures. So now we do have to think significant figure. We're not just the writer of the number or the calculator of the number. One, two, three, four, five, six. 1, 2, 3, 4, 5, 6. Okay, for those of you who already have your way of doing scientific notation, do it your way. I'm going to do it my algebra. How many significant figures are there? There's 4. That counts. It's a trailing 0 after the decimal. Where does the decimal need to be? It needs to be right here. 1, 2 away. If I do that math, I get 7.11, and I'm keeping that 0 because I need 4 significant figures. Times 10 to the 0. You with me? This equals 1. I put the negative 2 here because I wanted it to move this way, but I wanted the 10 to the positive 2 to be what survives over here. This one, I need to move the decimal 1 place forward. 10 to the 1 times 10 to the negative 1. I do that math, I get 2.39 times 10 to the 1. I should have pointed here and said, how many significant figures? 3. That means there's literally going to be 3 digits right here. How many significant digits? 5 here. The decimal is here, it's just not written. I needed to move back 1, 2, 3, 4. Negative 4. I do that math. I get 9.0743. This number and this number are equal to each other. Literally the exact same number. 4 significant digits. It needs to move back 2 do that math, you get okay? Do you hate my way of doing it? I feel this disdain. You don't look at me like, I'm not doing it like that. It'll keep you from making mistakes, I swear. Haven't you ever done that? You got the sign wrong and you just thought wrong? Come on, you've all done that. Doing homework on the test somewhere. I gotta move it forward, 1, 2. These are leading zeros, and you know those aren't significant. But those are gonna end up dropping off anyway. 1, 2, times 10 to the 2, times 10 to the negative 2. That gives me the 5.499, and I got this left. If I point here, and I say how many significant figures are here, you would say 4, and yes, there's literally 4 digits right here. It should always work out like that. How many significant digits is that? It is 6. Trailing 0 after the decimal, you know that counts. This is non-zero, it definitely counts. And it has to be contiguous, so those count too. So it's all of them, 1, 2, 3, 4, 5, 6. I gotta move this back, 1, 2, 3, 4, so times 10 to the 4 times 10 to the negative 4. That part gives me 1.00000. How many significant digits were here? And there's still 6. Would you have been tempted to drop all these off? Just make sure, when you look at the number before you do anything, you count the significant figures, make sure that's how many digits are here, 0 or not. 1, 2, 3, 4, 5, 6. How many significant figures are there? Yes. Again, I mean to have this for you all to see. Did you say 6? 6. Leading zeros don't count. 1, 2, 3, 4, 5, 6. The decimal needs to go 1, 2, 3, 4, 5, 6, 7 forward. So 10 to the 7 times 10 to the negative 7. This part gives me 7.38592, and then I have 10 to the negative 2 left. 7. Derp. 7. You guys okay with that? All right. I don't think there's examples in your book for this, given the way I like to draw out the powers of 10. You have that, and you have to multiply it by kind of back in my day, we didn't have scientific calculators that you could put powers of 10 in. And I had my strategy for solving something like this. And I still do it, so I'll just show this to you. Orders of operation don't matter for multiplication. So I can rearrange this as 1.67 times, there's this in scientific notation, there's this in scientific notation, and I'm saying you multiply them together. So it's this times this times this times this. I take the non-powers of 10 here, and then 10 to the 3 times 10 to the 9, and then this I can easily do in my calculator. This I do just by inspecting the powers. So this is going to be 10 to the 9 times 12. I'll put that multiplication symbol still here, and that I'm just going to do with my calculator. I don't know if these calculators do that power of 10 stuff for you, and put it in scientific notation for you. You'll have to investigate those. 1.67 times 6.14. My calculator says three significant figures. I'm keeping those. The 5 rounds the 2. So my answer to all of this is 10.3 times 10 to the 12. And yeah, I realize it just so happened I ended up with an answer that had a power of 10 in it. It's in scientific notation, it's just not in standard scientific notation. So what I'm going to do it my way, you hate me for it. 10 to the negative 1 will get it where I want it. 10 to the 1 has to be there to balance it, so I'm just multiplying by 1. And now, that's what I'm going to do. 10 to the negative 1 gives me 1.03, bringing that down. 10 to the 1 times 10 to the 12 is 10 to the 13. And that's my answer in standard scientific notation. 10 to the 12. Okay. 10 to the 3 was this part. 10 to the 12 came from this part. This part gave me 10 to the 3. This part gave me 10 to the 12. And that equals this, 10 to the 13. I know you're probably thinking, well, all I would have done is just block that out and add 1 there. But I'm telling you, when you do it in your head, it's where you make mistakes. So that's why I go through the tedious algebra way. But what I was showing you is, if you're multiplying a number that already has a power of 10 to it by another that already has a power of 10 to it, and your calculator is not going to let you enter a power of 10 for it, that's a good strategy. You just separate them out. That you can do easily with arithmetic. This you put in your calculator and you do your significant figure stuff, and then you fix it up at the end with my trick. I can tell you all do that. Let's see if there were any of those. It didn't do any where you're multiplying by power of 10. All right. I just brained it all of a sudden. 345 or 440? 415? 4 what? 445. What else did it do? Okay, I know where we are. Having said all that, the next thing to introduce. So what I just did, I know I told y'all to start at measurements if you wanted to read, but really everything I just did was 1.5 and 1.6. Maybe I did some measurements because they start with how you read measurements. But where I want to go now is, so this is 1.4 measurements, base units of the SI system. I guess that's table 1.2. How many of you have never seen this metric system stuff before? I'm guessing all of you have. Truthfully, in this list, it's weird. Oh, there's the mole. In this list, we use meter, we use mass a lot, but we're usually working in grams, not kilograms. Seconds won't come up in anything. We do use Kelvin. I'll tell you this, there's no candelas or amperes in this. But moles, Kelvin, grams, and meter we'll use a lot. Are y'all good with these? Let's see. I should write. All right, let me do this. I have these in a PowerPoint from another textbook, but I'd rather use the ones from our textbook. Suppose I just. These long classes, man, let's start going brain dead. There. I will give you this on a test. You don't need to memorize it. So I'm not going to start by saying, just like reiterating what's in this chart. I will note, though, those units, none of these units, the meter, the gram, the kelvins, the moles, none of those are in this chart. You see that? These are the prefixes for those things. Getting things got started here. This introduces the idea of conversion factors. So I will upload this. I'm not sure what I'll call it. So this is a short PowerPoint. This, again, is that list, but it's pared down. It's removed. It's removed the amperes and the candelas. But even segments, I don't think we'll use. And then there's the derived unit for volume, which is centimeters cubed. That's the definition of 1 milliliter. And if you multiply that by 1,000, you have a liter. This is where I wanted to start. Okay. Length, mass, and volume. All right. So in this PowerPoint where you see at the top, length, mass, and volume derived, let me start there. So we have what we call the metric system, right? And then we have this other system that's like, gallons and yards and feet. That's not the metric system. We don't use those units. But you do have conversions from one to another. I wish I could get the projector in front of the camera. Just do this. Let me write some stuff on the board. Does your phone ever update and everything's all different? Mine just did it a few days ago and it's just making me nuts. So what you have for length there, let me write on the board. On centimeter, I will come back to inches. I will come back to the metric system because, like I said, even if all of y'all have seen the metric system, this class doesn't assume that you have. But I want to do a section on conversion factors. Miles. And 1 mile equals 1.6093 kilometers. I'm going to skip the angstrom for now. So I have what I need on the board. Do you remember a discussion about exact versus inexact numbers? Well, that's what I'm about to do. And this is, all of this is so we call these standard so standard is yards, inches, miles, feet, that's standard. This is metric, meters, centimeters, kilometers, that's miles to feet, so that's not, and then kilometers. So I'll say yards, inches, miles, feet and miles. So everything I just underlined is standard, standard variables, standard units. Okay. So if you walk up to a number and it's well, these are always about context, so let me just say, this, how many significant figures are here? This one is 5. 1, 2, 3, 4, 5. How many significant figures are here? This is the point. That's not one significant figure. It's infinite. That represents 1.00000. It's exactly 1. Yeah, I guess I can still start this way. All right. So I'll give you that on the test. You don't have to memorize these. But realize if I had if I ask you this question, I have 6.45 meters. Let me make that 645.7 meters. What is this in yards? What you need is a conversion factor between meters and yards. And you look in a chart and you'll see there's meters, there's yards, but this isn't the way you want to use it. What you're going to do is 1 meter over 1.0936 yards. That will work as a conversion factor. So you've got an equal sign, but you write one of these in the numerator and one of them in the denominator. Or you might use it like, you might use it flipped over. It depends on what you're trying to calculate. So you take what's in the chart, you put it in this form, and then you go 7 meters. And I'm going to put it over 1 just because it makes things symmetrical. So that is just this piece of information. And now I need a conversion factor that's going to turn this into equals yards. So you could read something like this, and before you even look over here to get this information, realize you could read something like that and go ahead and write this much. You know you're going to have this, it comes from over there. You know there's going to be a conversion factor. And you know you're trying to get to yards, so you go ahead and write yards there. knowing that there's going to be some numerical value there. You could set up that much without even looking for your conversion factor. You with me? Of course, when you do look over here to get your conversion factor, you're going to use that in one of these two forms, but you're going to use it in a form that makes the meters cancel. And so that means you want meters on the bottom because meters are on the top here. So I'm going to use this one. Okay, here's my point about exact and inexact. Now we have a math problem, and we just spent all our time talking about significant figures. But you have this one that I just added on my own, and you have this one. There. So we've got multiplication and division to do. This has 4 significant figures. This has 1, 2, 3, 4, 5, and we only see one there, and we only see one there. So which one of these has the lowest significant figures? Well, we've only got one. That means we're going to do this calculation and only have one digit at the end of it. Well, of course that's not correct. That's the point. These are infinitely significant. Those have infinite significant figures. When you look at a chart like this with the equal sign that gives you your conversion factors, the ones are infinitely significant, like by definition, because they're written this way. So what that means is, I usually just do this. That's exact, that's exact. Meaning we don't even have to look at it for significant figures. We're still following the same rule. I've got a 4 written here, 5 written here. What I really need to write here is infinity, infinity. There's an infinite number of significant figures there, infinite number of significant figures there. So these ones are infinitely significant. And these, they're the significant digits that you're looking at right now. So what we really have is 4 significant figures, 5 significant figures, infinite, infinite. So that's what our answer needs to be. You follow that? $6.4. What have I done? 645.7. 1.0936. My calculator says I want 4 significant figures, so it's these. The 3 does not round to 1, so 706.1 yards. That's the answer. I could put it in scientific notation, or standard scientific notation, but let me just hold off on that. So exact versus inexact. These are inexact, and these are exact. All right, and let me work on put this. So when it's metric to standard, that's everything in that top left thing that I took from that I wrote here. These were all metric to standard. Non-ones are you ignore the exact ones for significant figures. The non-ones you count for significant figures when you're doing a calculation with the conversion factor when it's metric to standard. All right, let me contrast that. Yeah. metric to standard. Okay, look again at these. Meters, that's metric. Yards, that's standard. So you would use this for a metric to standard or standard to metric either way. I just wrote it metric first, but if you're going between metric and standard, this is metric to standard, this is metric to standard, this is metric to standard. This standard to standard, this is usually true for standard to standard as well. Let me. Let me talk about that separately. Okay, let me write down another set here. Run out of space. I guess I'll write this too, but I'm just eating up our time now. 7x cubed. This is what I want. I'm going to add something. What's pints? How many pints in a quart? Is it 2? I never work in standard. How many pints are in a quart? What is it? Is it 2? Let's double check that. There's also cups and stuff like that. Yeah, it's 2. What about cups? 4 cups to a pint? It'll be worth it. Hold on. Okay. 2 cups to a pint. What is the abbreviation for cups? I don't even cook, so I don't know this stuff. All right, here's my point. Liters is metrics, meter is metrics. liter, decameter, liter, centimeter. That's metric to metric. This is standard to standard. This was liters. Gallon to liters. Standard to metric. Standard to metric. Standard to standard, standard to standard, standard to standard, standard to standard. Here's what I'm saying. When you're doing standard to standard, both sides are exact. Here I was saying that's exact, infinite significant figures, but this one has 5 significant figures. When you're doing standard to standard, that's exact and that's exact. When it's standard to standard, they're like definitionally exact. 4 quarts to a gallon, 4 cups to a quart. So that's exact, that's exact, that's exact. So I can't say it comes down to the 1 when it's standard to standard. Both sides of the equal sign are infinitely exact. You with me? So you don't even look at those for significant figures. Meaning, I want to erase some of this. So I can squeeze that here. I don't have room to calculate. How many? How many quarts are in 19.3 gallons? You need quarts to gallons. That's this. And you're either going to go 4 quarts over 1 gallon, or you're going to go 1 gallon over 4 quarts. It's going to be one of those. It comes from context. So you start with this number that you're given, 19.3 gallon. Put it over 1. You could go ahead and go conversion factor equals, what am I trying to get, quarts, some numerical value, quarts. You could write that much without going to look up at it. But we had 4 quarts to 1 gallon, or 1 gallon to 4 quarts. We need gallon on the bottom, so 4 quarts to a gallon. So now I've got to calculate. How many significant figures? That's 3. This is 4.00000 all the way out to infinity. So this one's infinity, and these are definitely infinity. And this 1 that I use, just to force this to be in the numerator, I just like it because it's symmetrical. I could just not do this and write the 19.3 gallons down a little, but I just always do that. So my point is, that's a non-1, but we're not going to count it for significant figures. All of our significant figures come from right here. So my answer needs to be 3. So when it's standard to standard, whether it's a 1 or not, it's exact, and it doesn't count for significant figures. When it's standard to metric, well, let me finish this problem. 19.3 times 4 is really all we're doing. I end up with 77.2 quarts. It's already in the right numbers, significant figures, so I don't have to do anything. Just realize this one, this one, this one, this one, this one, this one, and these ones, and this one, and this one, this one, this one, this one, those are exact. But also, this 4, this 2, this 2, this 4 are also exact. And this one over here is exact as well. That's exact. Because it's standard to standard, miles to feet. So that's exact. That's not 4 significant figures. That's infinitely perfect. I could put decimal 0, 0, 0, 0, 0 all the way out to infinity. Because that's the definition of a mile, 4,280. So standard to standard, whether it's a 1 or not, it's a perfectly exact number. You don't consider it for significant figures. Standard to metric. I just need some space here. Standard to metric. Well, I guess I still have some money on. 1 gallon equals 3.7854 liters. Let's keep that one. It's not correct. I don't know what that was about. All right, let's just keep that one. I've got some space. 1 meter equals this many yards. But I could go in the same way that you can do in an algebra class, as long as you do the same thing to both sides, the equal sign is still fine. So let me do this. I'm going to divide both sides by 1.0936. One, two, three, four, five. So look at those two. Both of those give you meters to yards. You see that? And they're both perfectly valid. In this case, now this is exact, and this is the 5 significant figures. Here we had 5 significant figures here. Now the 5 significant figures are here with meters, and now this is exact. And that would work. That would work just as well for a conversion factor. It really would come out exactly the same, whether you use this or whether you use this. The reason these are written the way they are, well, I won't go into that. But anyway, when it's metric to standard, one side is always a 1. There's just kind of no reason to do it any other multiple. These are like definitional. So that's where the 1s come from. But this is relating 2 different systems. Okay. The other variation is, so that's where we got to go next. Those are all exact too. So let's. If you're not used to these prefixes and abbreviations, look at it, but this means meter, this means centimeter. Here we need a metric to metric conversion, meaning we're going to go, without considering any conversions, I can go ahead and do this. Conversion factor that goes from meters to centimeters, and then the meters will cancel, I'll end up in meters, and I'll have some numerical value. You can do all that without doing anything else. What is the conversion factor for centimeters to meters? If you want to do it using a chart like this, So what that chart is telling you, so in the third slide here, where you see prefix, symbol, and multiplier, the multiplier column, so look at centimeters, is that what it is? Centimeters. That 0.01 that you see means that many meters. I wish I could get the camera to point over here. It says centi, and then it says C. Abbreviation, and just if you want to use this chart to help you do conversion factors, you got to figure out what the conversion factor is. Just realize that whole chart, you don't see meter anywhere in it. That's the base unit. Those just have all the prefixes in it. If we're dealing in meters, aka centimeters, this column tells you how many meters, meaning 1 centimeter is 0.01 meters. Rewrite that. That's the conversion factor. So what's in that column is the base unit. If we were dealing in liters, we would have 0.01 liters here and centiliters here. How many of you are comfortable with the metric system? Okay. I'm sure I'm boring some of you. But let me point out. Okay, let me go ahead and use this. 1 centimeter over 0.01 meters, so I can do this. That will give you the correct answer. This is exact, and like I said over here, metric to metric, both of them are exact. This is exact. You don't consider that for significant figures. If I pointed at this and said how many significant figures, you'd say 1. You'd say 1 there, you'd say 1 there. What's the point in doing this calculation if you're only going to have 1 digit over here? That's exact, that's exact, that's exact. This is where all our significant figures come from. So if I calculated this out, there would be 4 digits here. See what I'm saying? Okay, but let me point out. This equals, so just working with that conversion factor, 1 divided by 0.01 equals 100. I'll keep the units by going centimeter over meter, but that's not what I'm getting at. I can take this 100 over 1, and it still equals 100, right? That's a perfectly fine conversion factor to use here. But so is this. I mean, they literally equal each other. 1 divided by 0.01 literally equals 100, which literally equals 100 divided by 1. So I could do this. Those of you who are comfortable with this, is that what you would have done for this conversion? Or would you have done this? Which way does your brain work? This one? I tend to do this a lot. It's easier for me. You're nodding now. So I just wanted to point that out. Same way I flipped the metric to English one. I can flip this one too. All right, one other thing about what do you do if you have to go from one of the things that's greater than 1, like, what should I do? Mega, do something. Let's do kilo. All right, let me do this. Should I calculate this out? 100 just moves the decimal 2 places. That'd be the answer to this one. But let me do another one. So this one went from the base unit to one of these that's lower than the base unit. So if the base unit is 1, so we went from the base unit that's essentially 1 down to 0.01. Let me do one that goes to, let's do it the other way. Yeah. Millimeters. So what I'm saying is, if you look at this chart, I'm going from up here to powers of 10 that are positive. So there's kilo, 10 to the 3, 1,000. Down here to where the power of 10 is negative. What do I do? Milli? Yeah. 10 to the negative 3, 10 to the 3. So those of you who are comfortable with this, what's your conversion factor? Can you do that quickly in your head? Okay, so let me go through my process here. If you look at the chart under multiplier, the multiplier you'll see for kilometers is 1,000. And the multiplier you see for millimeters is 001. So millimeters, 001, kilometers, 1,000. What that means is 1 kilometer equals 1,000 meters. And this means 0.001 millimeters equals 1 meter. Now, that meters. Yeah, the multiplier is meters. The multiplier is meters. So my two conversion factors that I could use here is 1 kilometer is 1,000 meters, and 0.001 meters, this is supposed to be millimeters, is 1 millimeter. So I can use these conversion factors in tandem to solve this problem. Km, conversion factor. I'm looking for millimeters, so millimeters and some numerical value. I can write all that down before I even think about conversion factors. The conversion factors I've come up with is these two. I need kilometers on the bottom to get it to cancel. So I'm going to use this, but I'm going to use it flipped over. I'm going to go okay, cancel kilometers. Now I need to cancel meters because I'm trying to get to millimeters. So I need meters on the bottom. So I'm going to use this one flipped over. 0.001 meters is 1 millimeter. So kilometers cancels, meters cancel, now I'm in millimeters. That'll work. That'll calculate out the answer I want. Again, notice, metric to metric, metric to metric. That's exact, that's exact, that's exact, that's exact. And this one I used just to prop up the number is exact. All of our significant figures come from here. And if you just want to calculate it, 13.63 times 1,000, and then divided by 0.001. That shouldn't happen. I did something wrong. 13.63 times 1,000 divided by 0.001. What am I doing wrong? Come on now, I guess that's right. It will be a huge number, okay. What my calculator says is 1, 3, 6. Four significant figures is these, but this is always going to happen in the metric system. Everything else is going to be a 0. So this works just as it is without a decimal there. That works. So I use two conversion factors. I use the kilometer to the base unit meter, and I use millimeters to the base unit meter. And I just made the meter cancel in the middle. Is that the way y'all did it in the past? You use two conversion factors? Okay. That works, but I want to point out that you could, just working with the conversion factors, you could go, just do that part in the middle there. I wrote it correctly. If you do this, the meters cancel, and you end up with millimeters to kilometers. That's exact. They're all exact. 1,000 divided by 0.001. My calculator says that 1,000 times the south, 1,000 essentially. So I ran it over up here. Really, let me do this. A million millimeters to kilometers. But I'm going to rewrite this, but I'm going to write it over 1. So I'm going to put that. If I took this and inserted it here, I would get the same exact answer. So you can use them in tandem like this. Are any of you able to come up with this, some slick way, just looking at the...
Can you just use the powers, like, because
That's the next thing I was going to go through. But I know what you're saying. The weird thing is you got 10 to the 3 and 10 to the negative 3.
And then there's 6 away from each other, so it's 10 to the 6, right?
That's the way you think of it?
The
Yeah.
million,
But which one does the 10 to the 6 go with? The kilometers?
Like you multiply it to the like what you're trying to find the conversion of, right? Like 13.63 times 10 to the 6 would give you that in millimeters.
But if I had this, you're not going to put 10 to the 6 with the other one. That would be wrong.
Yeah, would it be negative?
But where would the negative come from?
Because there's 6 away from each other.
I know what you're saying. I do it this tedious way to show you how you could, because I'm going to give you that chart on the test. And the quick way to do it, if you're trying to go from, again, it's something with the power of the 10, the power of 10, positive power of 10, trying to get to something with the negative to the negative power of 10. And that introduces the idea of using two conversion factors. So you look at the chart and you go, the multiplier is 1,000. That means 1,000 meters. And the multiplier for this one is 0.001, and that goes with meters. So you've got millimeters and kilometers. That means 1 kilometer is 1,000 meters, and this means 1 millimeter. What you're saying, though, you could go kilometers, and the multiplier is 10 to the 3. 1 kilometer is 10 to the 3 meters, and 1 millimeter is 10 to the negative 3 meters. But if you just look at it and go, there's 6 here, are you going to put the 10 to the 6 kilometers as 1 milliliter, or 10 to the 6 milliliters as 1 kilometer? And I think you do by intuition. You just know that the millimeters are, so there's something systematic about that. So what I suggest doing, especially if you're new to this, if you're going from positive power 10 to negative powers of 10, use 2 conversion factors just like this. You got kilometers, then you go to meters, and then for millimeters, you go to meters. And then you set them up so the meters cancel. And then you can just multiply straight across. How many of you are comfortable with the metric system? I'm going through all these details because I know there was at least one person who said they never took chemistry. Have all of you worked with the metric system before? Should we just try to solve some problems? I don't know what those are. Let me try doing a couple of calculations, and I'll give you some of these to practice. And if you're running into trouble because I'm just droning on now and you can't listen. Okay, here we go. Number 72. 612 grams is how many milligrams? The reason we can get to the conversion factor very easily is because we're going from the base unit, grams, to one of the multiples. Grams to milligrams. How many of you think you could do these easily? You're not going to tell me. Open pictures. All right, 612. All right, so let's do this in a systematic way. I have to bring this up. Just for those of you who aren't used to this, I'll make this better. Grams isn't on there. The multiplier for grams is 1. What's the multiplier for milligrams? What is it? Did you say 1,000? Okay. That's because you know there's 1,000 milligrams in 1 gram. But that's not what it says on next to milligram. What does it say next to milligram? 0.001. So what I'm saying is to get a conversion factor for this, that multiplier goes with the base unit, grams. So what I'm saying is, this many grams is 1 milligram. But somebody went, it's 1,000. Well, the way they're thinking is, these are totally equal to each other. Do you see what I'm saying? If you divide 1 by 0.001, you will get 1,000. And later in the semester, when I need a conversion factor and I'm not telling you how to use this chart, I do that too, because that's the way my brain thinks. But let me continue with it this way. If you're new to this, what I'm telling you to do is grams, that's not on there. Milligrams, look at it, look at the multiplier, and go 0.001 base unit. It's not 0.001 milligrams. What's in that column tells you how many grams back to the base unit. It tells you what you're using milli. it's this many base unit to 1 milli. So the conversion factor is 1 milligram. Okay. And like I said, we're not having to go from a positive power of 10 to a negative power of 10, or from a negative power of 10 to a positive power of 10. So we can do this with 1 conversion factor. Put that over 1. I'm going to use this. I need grams to be on the bottom. It happens to be written that way. I might have used it this way, but it turns out the way I wrote it was already correct. Grams will cancel. We'll end up in milligrams. That's exact, that's exact, that's exact. So we need 3 significant figures. And if you just do it in your calculator, you're ultimately just going 612 divided by 0.001 without a decimal. You guys comfortable with these? You think you could just do them? Should I keep going? I'm afraid there's somebody in here that's not done enough of this to not feel comfortable, but I can tell I'm putting half of you to sleep, so you're killing the vibe, yo. I'm getting tired too. The second one is meters to centimeters. Next one is micrograms to grams, milliliters to liters. All of these are going back to the base unit. Those are easy. Let me do a couple more of these. And if you think you're in trouble, you should come see me or go to, we don't have an SI, right? Do we have an SI? That's what I'm talking about, SI. Have any of you thought about going to the tutoring thing if you need it? Just to remind you, it's perfectly fine to come see me. Nobody does that anymore. Okay. Meters to centimeters. What's the multiplier for centimeters? Meters. So 1 centimeter, 0.01 meters. So if I have 8.160 meters, that'll do it. That's exact. That's exact. That's exact. Ultimately, you're just dividing by 0.01. How many significant figures are here? 3. Let me double check. Maybe they put a decimal there. Nope, there's no decimal. So we need 3 significant figures here. If I do this in my calculator, my calculator says, oh yeah, this is a good note to end on. So that's fine, 3 significant figures. That shows 3 significant figures. Right? All right, let me show you one more thing that'll wake you up a little before you go. What if you did a calculation and it came out to some units, but it's 4 significant figures. You look at your input values, the lowest number of significant figures was 4. So you're keeping these. The 0 does not round to 0, so you're going to go, and then you're going to go, oh, wait a minute, I need to put the decimal there. Well, that would make 1, 2, 3, 4, 5, 6. Well, that makes it 3. I need 4. So what do? Anybody know? I usually skip this because it makes you forget it. It makes everything seem too complicated. What do? If you need it to be 4 significant figures, 3, 4, 1, and 0, then putting the decimal there or removing the decimal doesn't help. What do?
Put it in scientific.
Scientific notation is the only thing you can do. To put this in scientific notation, I need the decimal there. It's here, so 1, 2, 3, 4, 5. Still doing it my way. There, 4 significant figures. The only way to solve that problem, when your significant figures is somewhere in a little field of zeros before the decimal, there's only one way you can do it correctly. You have to put it in scientific notation. Did that wake you up? I can tell it didn't. Good. The problems that I've gone over, if you want to feel like, hey, am I caught up in this class or not? Go through those. I'll make a list of them. I didn't write them down as we did it. I'll list them and put them on D2L, just so you have something to look at to feel like you're caught up as far as getting towards the test. We might have to take a break in this class. Take a 15-minute break. All right, that'll be it for today.